Hi everyone. In this video, we're going to start talking about the normal distribution, and it's just another type of distribution of probabilities and uh, variables. So before we start in on the normal distribution, I'd like to quickly review our binomial distribution. Now, this is all review, so I'm just going to go through it quickly. Here's an example of a binomial distribution. We start out by defining our discrete random variable, and if you remember, discrete means that our variable is countable. So an example of a discrete random variable would be the number of girls in a family with 6 kids. So if you remember, P is the probability of success. So in this case, that would be having a girl. The probability of having a girl is half, or 0.5. These are your probability of a success. Q is the probability of a failure, which is also 0.5, a boy. We're talking about 6 kids, so N equals 6. And R are all these different 7 things that can happen. You could have 0 girls and 5 boys. You could have 0 girls and 6 boys. You could have 1 girl and 5 boys, 2 girls and 4 boys, 3 and 3, 4 girls and 2 boys, 5 girls and 1 boy, or all 6 girls. Okay, now I went ahead and plugged it into the binomial formula, which is how we find the probabilities of each thing happening. And I'm not going to go through that, but I just want to remind you that if we add up all these decimals, and I put it as a decimal, so the probability of 0 girls is 0.017, which is 1.7%. So if you add up all of these values, you are going to get, it's going to either equal 100% if you're looking at percentages, or the number 1 if you're looking at the decimals, because there's nothing else that can happen. If you're having 6 kids, these are the only things that can happen. You can't have 7 girls if there's only 6 kids. Okay, we're going to take this one step further, and what if I put this into a histogram? I'm going to graph it, all right? And all I did here was make the number of girls, or a discrete random variable, is the x-axis. We have 0 through 6. And our y-axis is the probability of each of those things happening. This first one is slightly off. It should be more like right about here. But so for example, the 1.7 girls, here's 0.02, so that's about 2%. So here's 1.7. The probability of having 1 girl was 9.4. Here's 1.10, which is 10%. So 9.4% is slightly below that. 2 girls was up at 23.4%. 3 and 3 was 31.3%, which makes sense, half and half. And then coming down. And what you'll notice about this distribution is that it is normally distributed. It is symmetrical. Here is the mean at 3. Sure, it works out that the mean number of girls is 3. And we could use multiply n times p times q and take the square root of that to get the standard deviation. But if you remember, the mean was equal to n times p. 6 times 0.5 is equal to 3. So that's where that mean comes from. So the mean is right here at the center. The peak of the normal distribution curve is always the mean. And then it kind of goes down symmetrically from each side. And because this is a normal distribution, the mean and the median are right here the same. Okay, the same value of 3. So in other words, if we were to add up all of this on this side to the left of the mean, these areas in the rectangles, which are the probabilities, that would 50% would be on this side, and 50% would be over here on this side. Okay, but most importantly, what I want you to take note of is that the probability is really our area under this graph, the area in the histogram. That is your percent or probability. It just depends how you ask the question. So I could ask the question, what is the probability that a family with 6 children would, so X is a family with 6 children, what is the probability that they would have less than or equal to 1 child? What's the probability that a family, I'm not 1 child, 1 girl out of 6 kids. So all of these X's are families with 6 kids. So what would we do? We would add up these areas under histogram. We're talking about people with one child or no children. Okay, that's less than or equal to 1. So we would have to add that 9.4 plus the 1.7, and that would give us the probability of a family having one or less child. Um, and that value is equal to 11.1. There's 11.1% chance of choosing a family with 6 kids where they have only one or 0 girls. Okay. Another way of asking it is what percentage of families with 6 kids have 1 or less girls? It would be 11.1%. So percent and probability are talking about this same space, this area under the curve. Okay. So let's try to keep that in the mind as we move forward into this next piece. Okay, so now we're going to look at a normal distribution, which is just another type of distribution of probabilities. Okay, the difference is we're going to change the type of variable we're talking about now. Now we're going to be talking about continuous random variables rather than discrete. What does that mean? It means our variables are not necessarily countable, or they don't have to be whole numbers. For example, the last example with the number of girls, you can only have whole number values of girls. You can't have 1.5 girls. But if we're looking at, for example, in this problem in yellow, I'm talking about the height of 10-year-old kids. Okay, that is continuous because you can never have an exact height. You can carry it out to decimals. All right. So let's say that I tell you that in the population, the mean height of 10-year-olds is 55 inches with a standard deviation, and remember that sigma sign is standard deviation, is 6 inches. How do we find the probability of different things happening? Well, we're going to have to use a very special z-table, which I'll get to in just a few minutes. Okay, so let's turn this off and see if this helps. Okay, here we go. What I've done now is just like in the previous example, I graphed it. Okay, this is a better table. So we went ahead and I graphed the fact that the heights are normally distributed. Now, because this is not a discrete random variable, I can't possibly list every number. So I'm going to start by just putting the mean of 55 inches right here at the center. And I've labeled the x-axis as the heights. And we can think of this y-axis over here as the probability. But the probabilities will be the area under this curve. Okay, so let's see what we remember about these standard deviations. So if somebody is 55 inches tall, they're exactly average. What if we ask ourselves, how tall is somebody who's 1 standard deviation above the mean? Remember, 1 standard deviation, we were told, is equal to 6 inches. So 1 standard deviation is about here. And we know that 55 plus 6 is equal to 61. So somebody who is 61 inches tall is 1 standard deviation above the mean. Okay. On the flip side, somebody who's shorter than the mean by 1 standard deviation is going to be 55 minus 6, which is equal to 49. So somebody who's 1 standard deviation below the mean is going to be 49 inches tall. So all these values down here on the x-axis are in heights of inches. Now I'm going to write its corresponding standard deviation up here. So someone who is 61 inches tall is 1 standard deviation above the mean. And that is what we call rather than a x value, we call it a z value. Okay, so someone who's got a z-score of 1 means that they are 1 standard deviation above the mean. So somebody's got a z-score of 1.0, they're 61 inches tall. All right. So someone who is 49 inches tall, they have a z-score of -1, and all the negative means is that you are below the mean, you are less than the mean. We denote that with a negative, and you'll notice here I'm always carrying it out to 2 decimal places, and we'll get into the reason for that in a little bit. All right, so let's try the next one. Someone who is 2 standard deviations above the mean is how tall? someone who is 2 standard deviations above the mean, and the way we write that is the probability that, well, I'm not going to get into probabilities yet. I apologize. Let's erase that in a second. How tall are they? They are 61 plus another 6, another standard deviation of 6 inches, brings us to 67 inches tall. So somebody who is 67 inches tall has a z-score of 2. Okay. Now, let's talk a little bit about probabilities, which are the areas under the curve. And if you remember, we had something called the empirical rule. And the empirical rule told us that when data is normally distributed, then 68% of our population will lie within 1 standard deviation of the mean. So what does that mean? That means that 68% of 10-year-olds are between the heights of 49 inches and 61 inches. All right? And that 68% is really this shaded area under the curve. This area under the curve is our percent. It's our percent or probability, depending upon how the question is asked. Okay? Why don't you take a minute and see if you can fill out the rest of that table with 2 standard deviations up to 3 standard deviations. Okay, so hopefully you got something like this. 68% are between the heights of 49 and 61 inches. So 68% lies between within 1 standard deviation. Okay. Do we remember 2 standard deviations? From here to here, all the way out to 2 standard deviations, we had 95%. And remember, things outside of 2 standard deviations, that's when they started to get unusual. So 95% is within 2 standard deviations. That means this purple shaded area, which includes the green, is 95%, 0.95. All right. And then lastly, we'll take a look at the 3%. Let's see if I can find another. That was 99.7% of our data are within 3 standard deviations. Outside of 3 standard deviations, it starts to get so unusual that we hardly even consider it. So, in other words, 99.7% of 10-year-olds are going to be between the heights of 37 inches and 73 inches. So, if we were to write this in some statistical language, for example, what is the probability that somebody, a 10-year-old X, lies between, you know what, I'm going to say X. What's the probability that somebody lies between the height of, let's say, 67 inches and 43 inches? Okay. We would rewrite that in its z-score. So that is the same thing as the probability that, and I'm going to pick a different color. Rather than writing X, I'm going to change that to a Z. So the probability X lies between 43 and 61, 43 and 67. 43 and 67. Well, 43 is 2 standard deviations below the mean. So this 43 changes to a z-score of -2. And we always carry it out 2 decimal places. And that means it is greater than or below, 67 is 2 standard deviations above. So we're changing from an x value to its corresponding z value. And the probability that a z-score will lie between +2 and -2, that is our 95%. Okay? So I'm going to take you over to one more screen where we're going to look a little more at these percentages. Okay, so here we are again. Now, one thing I'd like to have you take notice of is, what about right here at the mean? The mean equals 55. What is the z-score for the mean? Well, it's actually 0, because That's what a z is. It's it's the number of standard deviations above or below the mean. So if you're right at the mean, that is no standard deviations above or below the mean. Okay, so let's go back here. And what I want to do is I want to identify the percentages in each of these areas. So let's start right here. If we know that there's 95% between -1 and +1, I'm sorry, 68%. If we take 68 and we divide that by 2, 68 divided by 2 is going to equal 34 and 34. So that means that each of these areas is 34%. So we've got 34% here and 34% here. 34%. Does that make sense, I hope? Because the whole thing from -1 to +1 was 68%. So half of it is from 0 to 1, and the other half is from 0 to -1. So we have 34% in this bar and 34% in this bar. Okay, what about in here? Let's pick another color. So in here, this area here is going to be the same as this area here between -1 and -2 and the distance from 1 to 2. What percent lies here is going to be 13.5%. How did I get that? Well, we know from here to here, all the way out to here is 95%. So if we take that 95% and we subtract off the 68% in the middle, right? And then we take that value and we're going to divide it by 2 because it's broken up into 2 pieces. And that's how you get your 13.5%. 13.5. You can try that on your calculator. All right, and lastly, I'm going to let you try it on your own calculators, but this area here between 2 and 3, this area here, and its corresponding area over here. Now, it's not perfectly symmetrical because I'm human error, but it's supposed to be perfectly symmetrical. This is going to work out to be 2.35%. We'll talk about in class where exactly these numbers come from. But it's the remaining 5% divided into 2 parts, subtracting off this little bit that's less above and below 3 standard deviations. So this last teeny tiny bit, I know it doesn't look like it, it should actually be much smaller, is just your 0.15%. That's 0.3% lies outside of 3 standard deviations. It's just 0.15%, half of it over here and half of it there. Okay, so that's how it all breaks down. Why is that important? Well, we can start to answer some questions. All right, so let's get a little better color here. What is the probability that a randomly chosen 10-year-old is taller than or greater than or equal to 61 inches? What is the probability that somebody a 10-year-old is taller than 61 inches? Well, the first thing we need to do is change our x value to a z value. And we can do that because we've already done it. We can just look right up here. 61 inches has a corresponding z value of 1.00. So I'm going to rewrite this. This is the same thing as z is greater than or equal to 1.00. Okay, and then I can see by adding up everything greater than 1.00, that's my 13.5% plus 2.35% plus 0.15%. Okay, and that is all going to add up to, oops, what's happening? Equals 16%? 16. Oops, 16%. Okay, so in other words, 16% of our children under the age, 10-year-old kids are taller than 61 inches. All right, let you guys try one. See if you can find the probability. We'll try a betweenness. Find the probability that somebody is taller than 37 inches and shorter than 61 inches. See if you can do that one. Take a second and see if you can figure that out. Okay, hopefully you worked out 83.85%. You saw that you changed it from 37, which is 3 standard deviations below the mean. 61 is 1 standard deviation above the mean, so you changed from an x to a z. And then you could see that that was all this area from here to here, and you hopefully added up, sorry, from here to from here to here, here to here. So you added up the 2.35 plus the 13.5, I guess I never wrote that here, plus 130, plus the 34 here, plus the 34 here, and all that added up to 83.85. Okay, so what you may start to wonder is, what if it's not exactly a whole standard deviation above or below? Okay, then what happens? And that is what we're going to start talking about in the next video. So, for example, what if somebody is 62 inches tall? What if somebody's 62 inches tall? What's the probability that somebody is taller than 62 inches? Okay, that becomes a little tricky because 62 is not, we don't know how many standard deviations that is above the mean. We know it's more than one, but less than two. And we need to go ahead and try to figure that out. So go ahead and try some of these, and we'll link to the next video. Good luck.